Our final awardee presentation is by Dr. Terrence Alger from Southwest Research Institute. Dr. Alger is the director of the Powertrain Engineering Division at Southwest Research. His work on vehicle engines is already resulting in lower levels of pollution and better fuel economy. Everybody's trying to do away with my job. I don't understand this. He developed a technology known as dedicated exhaust gas recirculation, where exhaust gas from the engine is given back to the fresh air being drawn into the engine. He'll explain this better. This technology improves fuel economy up to 15%, while also increasing engine performance. Dr. Alger's work will help lead to a more sustainable transportation future and will make a big difference in how clean and efficient everyday cars are on the road. Dr. Alger.
All right, thank you very much. It's very nice to be here. I realize I have a couple of challenges. The first one is that I'm the last talker, right? So it's been a long day, and I appreciate you all hanging in there. And the second challenge is, I think, put really well by Henry Ford, who's the current chairman of Ford Motor Company. And he said one of the worst jobs in the world is to work on cars because absolutely every person has one, and they've got at least a couple opinions on how to make it better. So I'm going to talk about some stuff with a car, and I'd be happy to hear your opinions on what you think when we get done. Unlike the previous speakers, I'm going to thank everyone first, mainly so I can absolve them of anything that I say afterwards. So I'd like to thank Southwest Research Institute. The company that I work for has been very supportive. They've given me the latitude to pursue my work, irregardless of sometimes the rather considerable budget I ask for when we're going to do some of these projects. So I'm very grateful for their support. And then Southwest Research Institute runs a consortium of auto companies and automobile supply companies that fund most of the work that we've done here that's resulted in this new technology. So we talk about the future challenges, and I mean, it's not nearly as bad as the two-bucket disease, maybe. But the challenge for the auto companies is considerable. In 2008, when the price of oil went up and gasoline was $4 a gallon, we proposed some fuel economy standards. Those got readjusted in 2012, and then on top of that, we got a new emissions standard. And so since 2012, with an end date of 2025, our automobile manufacturers are expected to increase the miles per gallon by 58% while reducing their pollutants by 81%. And that's a considerable amount because current cars are already really clean, and considering the amount of mass they move down the road, they're already pretty efficient. And at the same time, because it's a consumer good, we've got to do it at a very low cost, and we've got to make everybody happy. So it's quite a challenge facing the automobile industry going into 2025. So the first thing that comes back is, well, that's it. The internal combustion engine's dead. And if you look on Google or Yahoo News or any of those news sources, you'll see article after article saying that lights out, it's the Betamax of 2018, right? Well, not so fast. I think if you look at future internal combustion engine powered vehicles, and this graph kind of shows, this is taken for some work done by Argonne National Laboratory. When we start applying these future technologies like the one I'm going to talk about today, what we find is that if you really care about CO2 emissions and you start looking at the life cycle CO2, so the cost of digging that lithium up in Venezuela and shipping it to China and turning that into a battery and then shipping that back to the United States and then generating a bunch of coal or natural gas electricity to charge the battery and all of that stuff wrapped up together, well, a really efficient internal combustion engine with or without a few batteries can look just as low in terms of CO2 as a battery electric vehicle. And so our task is to keep pushing the limits of what we can do with an internal combustion engine. I think some engineers from Toyota told us the other day really well, they want to squeeze every bit of energy up out of every drop of oil that they can. So if we want to make the internal combustion engine more efficient and cleaner, we go back to our first principles. As an engineer, I'm not big on math in particular, but I do use the Otto cycle formula. It's only got 2 variables, so I feel pretty safe. But if we look at the Otto cycle, we find that the only 2 things that really impact the efficiency of a car engine are the ratio-specific heat to the working fluid, which is air, and the compression ratio, all right? And if we want to do something about efficiency from a fundamental level, we have to make sure we improve our compression ratio as much as we can, and we help out our ratio-specific heats to the extent possible. Now, practically speaking, the internal combustion engine's got a bunch of other losses. If you think about your engine as just a big air pump that you heat the air up while it's going through that pumping process, there's some work associated with moving that air through the engine. And that's where you find out these variable valve train engines that are so hot on the market right now. They go into trying to reduce that pumping work as much as they can. Friction is very important, and all of the oil companies are working as hard as they possibly can to make super slippery oils that we can put in our engine and reduce the friction that way. But what we're interested in is the thermodynamic part of this equation, which is limited by knock. And so if we really want to reduce the heat rejection, if we really want to improve our thermodynamic efficiency, we need to do something about knock. And I guess, nothing in this world is new. In the 1970s, Nissan took a look at using exhaust gas recirculation to reduce knock in an internal combustion engine. And it was a failure. But it wasn't a failure because of the first principles. It was a failure because they didn't have electronic engine controls, their ignition systems weren't state-of-the-art. And so in 2003, Southwest Research Institute was doing a bunch of work for the federal government on a grant, and we reinvented CoolDGR. We took another swing at it in a natural gas engine for power generation, only this time we had the advantage of electronic engine controls, of really good turbochargers, and a really robust ignition system. And what we found was that CoolDGR is a wonderful way to improve the efficiency of a gasoline engine. So in a nutshell, you tap into the exhaust of your car, and you take the burned gas, and you run it through a heat exchanger to cool it down, and you put it back into the intake. And it's kind of nonsensical when you think about it. One of the VPs at a car company up in Detroit one time, when I was first introducing him to this idea, told me he felt like he was being asked to drink out of a toilet. And so, there's some things you have to get around. We're going to use burned gas back in the engine, but it does a very, very good job of suppressing knock when you add it into the engine in its cooled form. And so for the first few years of our HEDGE consortium, we spent a lot of time showing the car companies that were members of this consortium how beneficial CoolDGR could be to them from an efficiency standpoint. And you can increase the compression ratio of the engine. It cools down combustion considerably. And if you're a thermodynamicist, you know that the ratio of specific heats is a function of temperature. So the cooler you can be, the better off you are. So now we've achieved our 2 fundamental goals. We've introduced CoolDGR. We get a better ratio of specific heats, and we get a higher compression ratio. The problem is that when you do that, you end up slowing the flame down in the engine. And that leads to a reduction in the stability. And if you've ever had a car that idles really rough, and you can hear the engine kind of making chugging noises, and you feel the vibration in your steering wheel, you know that nobody wants to deal with an unstable engine. So around this time, it was about 2003, 2004, President Bush was telling us about how the hydrogen economy was going to save the world, and we're all going to be having fuel cell vehicles now, actually, I think. Anyway, it didn't work out the way he wanted, but hydrogen was a pretty hot topic. And a lot of researchers at MIT and other universities were looking at ways to turn gasoline into hydrogen. Now, unfortunately, all those techniques failed for various reasons. But we started thinking about, well, if we could take some of that hydrogen and put it into our gasoline engine, wouldn't that be awesome? Because hydrogen's a magical fuel. So we started looking at ways to reform the gasoline and couldn't come up with any satisfactory ones that would meet the criteria of being cheap and robust and durable until we sat down and we said, well, we know if we burn excess fuel in the engine, we make a lot of hydrogen. What's to stop us from taking one cylinder of the engine and separating the exhaust out, because your catalytic converter doesn't work with anything other than a perfect ratio of gasoline to air. So that rich combustion will destroy your catalyst. But if we separate this guy out and we start making hydrogen in this cylinder, and you can see the hydrogen's represented by the bubbles here, and then pump it back into the engine and send it to every cylinder, what happens then? Can we make enough? Does it work? Is it totally ridiculous? And the answer is it works really, really well. So why does it work? It works because carbon monoxide and hydrogen are wonderful fuels, in particular the hydrogen, although don't slight the carbon monoxide a bit. So hydrogen has an outstanding knock resistance. If you all go to the gas station, you know you buy the 87 octane, most of you, unless you drive a Lexus. I saw a lot of those in the parking lot. That's a 93, right? But hydrogen is 120. So if you can get that kind of knock resistance out of hydrogen, you're really in business. It's also got a very, very fast flame speed. So that degradation in burn rate that we get from adding the cooled EGR, we can make up a lot of that with the hydrogen that we put into the engine. And the last thing is, it's wonderfully tolerant of dilution. Now, that makes it a very dangerous thing, which is why no one wants to have a bottle of hydrogen on their car, because the flammability limits of hydrogen are so wide. But if you're just making what you need inside the engine and it's all contained, that's perfect. So we end up with these two fuels that have pretty good dilution tolerance, very good knock resistance. Carbon monoxide is 106 octane, so it's almost as good as hydrogen, but not quite. And we can make them in a sufficient amount, then we can improve the way the engine runs. And if you burn 40% excess fuel in that one cylinder, you can put about 1.5% by volume hydrogen into your intake manifold. Doesn't sound like a lot, but it's enough to do the trick. And conveniently, it's also just below the flammability limit, so you don't have to worry about your intake manifold catching on fire. So we put it into an engine, and this is, if you're not an engine person, which none of you are, but I had to listen to a whole day of brain talk, so we'll go here. What you can see is that you start out with no dilution in the engine, and this is a histogram of burn rates. So what you want this thing to do is be really narrow and really off to the left, okay? What you do is you add recirculated exhaust gas, the distribution of burn rates gets wider, so more variation from cycle to cycle, and slower, all right? And that's just bad for stability. So then we add that little bit of hydrogen back in, and we get this dotted line. And really the takeaway is it almost gets us back to having no EGR in the engine in terms of stability. So it stabilizes the engine wonderfully. We can add 20 to 25% recirculated exhaust gas from idle all the way up to rated power without any concern about unstable operation in the engine. And the other thing it does is it gives us about the equivalent of going from regular unleaded to premium. Okay, so we get about 4 points of octane by adding that small amount of hydrogen and carbon monoxide back into the intake manifold of the engine. So it truly is kind of a magical result, and it was fortuitous that we happened to think of it. I'm not going to claim that it was more of a lucky discovery than anything else. So then we decided to take and really think about what could we do with this, right? Because if you look here, some level of electrification is going to be on the car in the future. There's no way we can get to 54.5 miles per gallon without some form of an electric machine on the engine. But what we want to be able to do is burn gasoline like a diesel. And I don't mean we're going to cheat on the emissions. What I mean is that we are going to have diesel-like levels of efficiency. So this is actually a Honda hybrid electric engine that we took, and we converted it to run like a dedicated EGR application. And what we end up with is fuel consumption below the diesel fuel consumption range. So just purely in terms of thermal efficiency, our dedicated EGR engine at ultra-high compression ratios with cold combustion is burning more efficiently than a diesel engine, and we can make more than enough torque to satisfy the requirements of a hybrid electric vehicle. So that's great. So we took these results and we went out to all of our car company friends and we said, hey, this is the greatest thing since sliced bread. You're going to have to do this. And they said, well, that really looks great on a test bench, but I can think of a million reasons why I don't want to do this, because what's it going to look like in a vehicle? So then I went back to our company president and I said, I need $2 million to build a vehicle. And fortunately, they said, okay, we'll give it to you a little chunk at a time, but you can have it and you can build this vehicle. So we took a 2012 Buick Regal, mainly because we were in the middle of a program with General Motors funded by the Department of Energy to look at this in a Malibu. So Malibu and a Regal are pretty similar. And we converted it to run with our dedicated EGR engine. So we tested the engine in its base form, which was a 2.4-liter naturally aspirated gasoline direct injection, state-of-the-art technology engine. And it's a pretty good car, right? Got 25 miles per gallon in the city, which for a car that weighs as much as this one is pretty good. And 44 miles per gallon on the highway, which is pretty decent. And the NOx plus hydrocarbon emissions out of the tailpipe were 42 milligrams per mile, which, frankly speaking, is so close to zero that you might as well just be zero, right? So it's a very, very clean car. Well, once we converted it to dedicated EGR, what we saw was about a 13% improvement in city fuel economy, and that's because we were able to take the 10-to-1 compression ratio engine and bump it up to 13-to-1, which is a significant improvement in its Otto cycle efficiency, and all the other benefits we got from our dedicated EGR engine. Highway fuel economy was about 10% better. So again, that's all compression ratio and knock resistance improvement. And we even improved the emissions, which was a challenge. So right now the US government regulates you in terms of NOx plus hydrocarbon. But if you know anything about car engines, when you add dilution to the car engine, the hydrocarbons don't change much, but the emissions of the oxides of nitrogen drop like a rock. So we had effectively zero NOx emissions, and then our hydrocarbons made up the balance there. So it was great. However, the most important thing that happened as a person who really likes cars is that we did all of this while improving the 0 to 60 mile per hour time by 1 second. So not only, if you remember that one bubble at the bottom, we had customer satisfaction, right? So not only do we make the car cleaner, not only make it more fuel efficient, but we made it more fun to drive. And Buick Regal and fun to drive don't usually go in the same sentence, but in this case, it was pretty fun, okay? So what's next? So we've just demonstrated that it's in a car. We're talking to all our partners. It is being developed for production applications by the people that we work with, so we're very excited about that. But the internal combustion engine has a lot of room to go, and so we work on the combustion side mostly. So we're working on ways to make the internal combustion engine burn better. One of the ways we're doing that is by improving the ignition system. So the HEDGE program has generated 2 R&D 100 awards. The first one was for our dual coil offset ignition system that we invented in the program. It's a new way of running a spark plug that substantially improves the dilution tolerance. The second one was for dedicated EGR. So we won that award in 2014. And we're hoping that our latest thing, which is microwave enhanced combustion, is going to be the next one. And so I challenge all of you, when you get home tomorrow, or if you get back to your hotel room and it's got a microwave, you can try this there. That might be better than doing it at home. Light something on fire and stick it in your microwave. Turn it on and watch what happens. So again, Southwest is a great place to work. I have a lot of time to think about stuff and try things out. And so one day we were watching YouTube in the conference room and, hey, look at this. Somebody lit something on fire and put it in the microwave. That's awesome. Let's go try it. So we ran out. We bought a microwave, went down to the lab. We just lit things on fire and threw it in the microwave. And sure enough, it increases the burn rate of whatever you've got in there by a substantial amount. It's amazing. So we said, what are we going to do next? we're going to figure out a way to get that microwave into the internal combustion engine, and we are going to promote burn through not only the presence of hydrogen and CO, but by a standing microwave field. And so right now in our program, we've got, again, another Buick engine with a microwave antenna that Southwest designed, and it's sticking into the cylinder, and we've been putting those microwaves into the combustion chamber, and it is improving the burn rate. Now, we've got a long way to go before we can conclusively demonstrate this, but I think, if nothing else, what this should tell everybody out there, the next time you hear that the battery is going to put an end to the internal combustion engine, think about all the things that we've been doing over the past 15 years to improve the engine, and we've got another good 15 or 20 years worth of research left in us at a minimum. So yes, batteries are improving. I also run the battery activity at Southwest, so I've got to say, hey, don't forget that. But the internal combustion engine's got a lot of life left in it, and we've been doing some great things at Southwest Research Institute to try to improve it. So with that, I'll take whatever questions you have, and thank you very, very much.
We have time for a few questions. I'd like to ask one.
Okay.
When are you going to get to the point where when I drive my Buick in LA, I clean the air?
Well, we're there. A fully warmed up car with a functioning catalytic converter, maybe has 1 part per million of the oxides of nitrogen coming out, and functionally no carbon monoxide or unburned hydrocarbons. So I'm not even sure you could kill yourself with your car if you tried. So.
Yeah, so I had a quick question on the 0 to 60, which I think is because of the performance of the battery rather than the engine, if I'm correct.
So that car did not have any, it had a 12-volt battery for the starter and stuff, but it didn't have any hybridization.
Okay, so you actually got the torque directly from the engine. Okay.
So one of the challenges is if you turbocharge an engine, you can get a lot more power and it goes real fast, but the fuel economy takes a dive.
Right.
With what we do with dedicated EGR, because we suppress knock, we can turbocharge the engine and not have to drop the compression ratio because of knock and not take that big fuel economy penalty. So that engine was turbocharged. It was making about 80 kilowatts per liter, which is a substantial amount of power per displacement, but doing it at a 13-to-1 compression ratio. So very, very efficient.
But was the drive that you would have, was not a direct, was it an electrical drive to the wheels?
No.
Okay,
Because
the diagram that you showed actually was basically a hybrid, basically, with a battery, which I think gives you really spectacular 0 to 60 performance.
The hybrid vehicles do have a very good, especially if they've got the electric motors connected right to the wheels, like that. Yeah, it's amazing 0 to 60, So, yeah, but this one was not a hybrid. Yes, sir?
Fascinating talk, thanks. You didn't tell us what the 0 to 60 time was. I think it's about 12 seconds.
It's still a Buick Regal, so.
The question I wanted to ask was on August 23rd at 3 o'clock in the afternoon on Highway 45, what do you do with all the heat that you have to remove from the exhaust system?
So that is a challenge, but the heat is going someplace anyway, right? So at light loads, it's typically not such a big deal. We often find that the heat soak on the charge air cooler is more challenging than the heat removal from the radiator. Now, if you're running at full power for an extended period of time, it does become a difficulty. One of the things we're looking at now at Southwest is using a waste heat recovery device developed as part of a different program to take some of that waste heat and turn it into usable energy rather than just using it all in the heat exchanger. And so maybe, who knows, in 10 years, one of my colleagues will be up here talking to you all about our new waste heat recovery device that we've developed as part of our supercritical CO2 program. But yeah, it's not an inconsiderable challenge, but one of the reasons why we built the car was to prove to people that those challenges were manageable in a vehicle platform.
Okay, thank you very much.